let's continue at last. So today I'm going to talk about product, measure, and Fourier theorem. Now, we have developed the measure and integration theory, Lebesgue theory, on the line, one-dimensional. Now, I want to do it in higher dimensions. No, it is enough to do it, say, in the square. And then it will be clear how to do it in any dimension. So, consider a square in the xy plane. It is 0, it is 1, it is 1. It is our domain x. It is the square. And now I have to introduce again the sigma algebra of measurable sets here, and the measure. Introduce the measure in the square. Developed all this theory. No, mostly it goes the same way, but with some interesting variation. So I defined elementary set. It is rectangle. It is rectangle, x between A and B, y between C and D. Let me call it R. So we have this rectangle, and a rectangle can be this, or they can be A less or equal than B less. Let me write the following: less or equal, or less or equal, less or equal, less or equal. So all to 16 combinations of these signs that are also they called elementary sets. Now we have the following thing. Rectangles is the most elementary set, and a set A is called elementary, if A is union of finite number of rectangles Ri, I from 1 to n, and which are disjoint. This means Ri, Rj equal A if I different from J. So it can be looked, for example, like this, or it can be something like this, and so on. So these all are elementary sets. Now I wanted to introduce the measure of this set. So measure, let me denote it lambda of R. R is this, equals P minus A times D minus C. Like a measure of ordinary rectangle in ordinary geometry. And now I define lambda of A. A is this set, equal sum lambda of Ri, I from 1 to n. If these Ri are disjoint. Now, what can be said about, say, the union of two rectangles which are not disjoint? Let me draw a picture without formalities. So we have, this is R1, and this is, say, R2. Two rectangles, and their union, R1 union with R2, equals, so we have to subdivide it into smaller rectangles. So all in all, we have here 1, 2, 3, 4, and 5 rectangles equals let me write R Roman 1 union R Roman 2 union R no Roman 5. Yeah, so we have this thing, and we can see easily the following thing. And one moment, R1 intersection with R2, it looks like this. No, it is rectangle, equals R3. So it is rectangle, no problem. And say R1 minus R2. Now in this, let me draw this picture. It is R1, it is R2, R1, it is R2, R1 minus R2, it is this domain, which is also union of 3 rectangles. Yeah, so it is also elementary set. And other things are 1, symmetric difference R2 equals R1 minus R2 union with R2 minus R1. Yeah, so this is no, like this. Let me draw a similar picture. It is this 1, 2, 3, 4, 5, 6. No, we can unite it in one rectangle, this in one rectangle, it's okay. This is so R1 symmetric difference with R2 equals R1 Roman union R6 Roman. And the following, the first, and so we can define measure of, say, R1 union R2 equals some, say, measure R Roman 1 plus and so on, plus measure of R how many Roman 5. Lambda R1 symmetric difference with R2 equals lambda, it is here. No, it is here, this picture. It is lambda of R Roman 1 plus and so on, plus lambda of R Roman 6. Yeah. So we can define it quite easy. But here we have one interesting question. If you have, say, this set, we can subdivide it into non-overlapping rectangles in different ways. Yeah. No, even if you have just one rectangle, we can subdivide it something like this. Yeah. This is, for example, some division. And we have to make sure that after every such subdivision of, say, one rectangle, the sum of the measures lambda of this constituent smaller rectangle equals to measure of the whole rectangle. Yes? And if you have any operation with rectangles and have a domain which is a union of several rectangles with any sort of their mutual configuration and position, that the result will be the same however we subdivide it into smaller rectangles. Yeah, and so this means that we have to prove the following lemma. That A equals union Ri, I from 1 to n. No, finite number of rectangles, but they are not mutually non-overlapping, so they can have common parts. First, A can be subdivided into finite number of rectangles, say A is union, say Q, J from 1 to M, yes, such that Q, J, QK is union if J different from K. Yeah. So first we can subdivide it into finite number of non-overlapping rectangles, and second, lambda of A equals sum lambda of Qj, j from 1 to m, does not depend on the partition. So we can subdivide it in different ways, in different number of rectangles, different sizes and shapes, but the total result, this measure of all lambda, no, for example, in this case, we can start from this, how to prove that the area of this rectangle, which is product of two sides, is equal to sum of the area of these smaller rectangles. Yes, however we subdivide it, the result will be the same. You know what? I would prefer not to prove this lemma and leave it you as a problem. I did not give you problems for some a long time, so now I will leave it as a problem for you. Starting from this and then prove it. No, first the first part and then the second part. No, I think that the first part can be proved by induction. So, and the second part, no, okay, just and then we will see how you did it. And now we have the definition. First definition. M is the set of elementary sets in the square. Yeah. So the sets which are unions of finite number of non-overlapping rectangles. And if so we have the following property, say A, B are elementary sets, then first A union B in M, second A intersection M, 3 complement, no, the whole square, let us call this square, say E, the square E, E minus A in M, or E A minus B in M, A symmetric difference with B in M. Yeah. So this means that these sets, elementary sets, form what is called M is semi-ring. Yeah, no, semi-ring of sets. I don't know why this hypothesis, but okay. Now I wanted to introduce the wider class of sets, which I call measurable sets. First of all, I introduce upper measure. Lambda star of A equals, so A is any subset of E, upper lambda star of A equals infimum lambda of B, such that B in M, so it is elementary set. No, it is not elementary set. Equals infimum sum lambda of BI in principle it is countable such that BI in M and union BI contains A. Yeah. So we cover A with by union of countable number of elementary sets. Yeah. No, each elementary set is consists of finite number of rectangles, so we can consider these sets BI just rectangles. It's after all the same. So it is the upper or external measure of A. It is the first definition. The next definition is the following. A is measurable if for any epsilon there exists a set B equals union BI, countable number of sets, BI in M, such that upper measure of A delta B less than epsilon. So a set is measurable if it can be approximated by countable unions of elementary sets. Now let me introduce notation if I did not do it. Say M bar equals set union BI such that BI in M. Yeah. So we have this. So A is measurable if for any epsilon there exists a set B in M bar such that the upper measure of A symmetric difference with B less than epsilon. So this is the definition of measurable sets. And now the next thing is the following. The measure, the upper measure, lambda star, has the property of subadditivity. Of A union B less or equal than lambda star of A plus lambda star of B, which is obvious. Yeah, and then exactly like we proved on the line, we have the following. One moment. I have to define. So I defined the upper measure. I defined the measurable sets. Now I have to define a measure for the measurable sets. To this end, I have to define the measure on M bar. A in M bar, we can write M, A is union of BI BI in M. Yes, it's union of countable number of elementary set. So A is, say, B1 union B2 B2 minus B1, union B3 minus B1 union B2, union and so on. Equals A1 union A2 union and so on. Again, all this measure, this set is also elementary because it's the difference of elementary set. This is also elementary and so on. So all AI are elementary, and AJ is empty. So at every step we add a new elementary set which have no common point with previous ones, and then we define lambda of A equals some lambda of AI. It is the measure, and then we prove that this measure is defined on the set M bar. Yes, so M bar is the collection of measurable sets. Yeah, so it is all measurable sets, and the next theorem, lambda is a countably additive measure on M bar. Yeah. And again, it is proved exactly like it was done on the line. On the line, elementary sets were collection of finite number of, say, intervals. It was M. M bars are the unions of finite, countable number of elementary sets, or the same countable number of intervals, and then on the if you consider collection of measurable sets such that they can be approximated by the sets from M bar arbitrarily with arbitrary accuracy, in sense of the upper measure of symmetric difference between set of M bar and set A, then this set A is called measurable, and for the measurable sets we have this countable additivity, which was proved. It is all the same, and I'm not going to repeat it now because I wanted to go to the today's contents of today's lecture. So we have already a measure lambda, which is defined on some sets in the plane. Now a little later we'll see how what is this set. Now we can go to the plane, the whole plane, we did it now in the square, but now we consider the plane R2. It is x-axis, it is y-axis. We divide it into equal square of size 1, for example. Define lambda in each of these squares. And if you have a set which does not fit in one of these squares, no, we divide it into the parts, intersection with each squares, and define the measure of two-dimensional measure of this set as the sum of measures of this square. So it is E km. It is this square E km. K less than x less than k plus 1. M less than y less than m plus 1. Yeah. And consider A is union A intersection with E km. Km. And we say that A in M bar, if A intersection E km in M bar, no, in this rectangle. Yeah, so this is definition, and lambda of A is the sum lambda of A intersection with E km. Km. Yes, but this is mostly less interesting, so we can mostly consider what happens in unit square. Now, what can be said about these measurable sets? Let A in E be an open set. Yeah. Then A is measurable. So open sets are measurable. Now, why? First of all, first, suppose A is a domain with smooth boundary. Yeah. So what we do with this domain with smooth boundary? We divide it into small squares like this. And take the squares which are entirely inside this domain. Yeah. Let me sketch this part of domain. Like this. Yeah. Now let us take the remaining part of this domain and divide it into the squares of much smaller size. Yeah. Then again, some of these new squares will be completely inside this domain, and some will have intersection with the boundary. So let me call it, say, A1. This so here we'll have some set like this. Yeah. I don't draw all the internal lines. No, something like this. So this is A2. Remaining part, which is closer to the boundary, will be, we do the same. If something remains there, we divide it into much smaller size squares, and so on. And it is more or less elementary to show that the external measure lambda star of this set A, A2, A3, and so on goes to 0. So A equals union A, I from 1 to n, plus Bn, remainder. And this remainder has the property that lambda star of Bn goes to 0 as n goes to infinity. Yeah, so for domains with smooth boundary, it is simple. Now, how to reduce everything to this case? Now, we can consider, we have this open set A. Now consider A R equal a set of x, y in A, such, let me call it just x in A, such that distance from x to E minus A less than R. Yeah. For sufficiently small R, this set is not empty, and moreover, have the following thing: lambda A minus AR goes to 0 as R goes to 0. Simply because any point of this domain, so A is union AR for R more than 0. So when R goes to 0, eventually any point, because any point of the open set is internal set, yeah, internal point, X, some neighborhood of this point X is completely inside this set, and so the radius of this circle is that same R, so the X inside AR. And so union of AR is A, and because, no, we can take union, say, over N, ARN, like this. and say Rn equals, say, 1 over n, it's enough. Uh, uh, and so, because this set A is union of this set ARn, and ARn is an open set with a regular boundary. What does mean regular boundary? It means that this boundary is no, say in the square. This boundary is just smaller square. This is R. So it is, we first take this R, and then we a little bit smooth it, yeah, like this. Then we have the smooth boundary, and like here we have that this is A R in M bar. No, yes, I think it is a good domain. No, you can think a little bit about this. Yes, so a open set, and because A is union of these things, and they are it is a growing set. A R n plus 1 is more than A R n. So we have the growing sequence of sets in M bar. Then, because of countable additivity, lambda of A R n goes, it grows and goes to lambda of one moment. Is it true? I hope it is true. So the morale is that any open set can be decomposed into countable union of square of rectangles. Yes. So it is true. Maybe it is also can be left as an exercise. So, okay, so if open sets are in this, each ARn is an open set, yeah? So the union of this is also an open set, and yes, it is decomposed. Each of them is decomposed in a finite number of squares. Yes, and the union that is A is decomposed in countable number of squares. So this means that A in M bar. A in M bar, And this means that any open set, and because it is an algebra of sets, any closed set, because they complement to the sets in M bar, is also there. Yes, it is also measurable. Any closed set is measurable. Why a closed set is measurable? Because we take its epsilon neighborhood and then take epsilon goes to 0, and so we have a good approximation of closed set by open sets. So it will be, it is also closed sets, and after all Borel sets, I mean the smallest sigma algebra, which is which contains open sets, and the smallest sigma algebra, it all inside the sigma algebra M bar. Yeah. No, the sigma algebra. One moment. The sigma algebra span by the elementary sets, yes, it is the sigma algebra of measurable set. M bar are simplest measurable sets. Yes, and sigma algebra, let me denote it. Let's denote by T. Sigma algebra of measurable sets in E. It is the square. And T contains Borel's of E. Borel algebra or Borel sets in E. But it contains also some something beyond it. Okay. Now so this means the following thing. In particular, T contains not only rectangles like this, yes, but it contains also this turned rectangles, yeah. So after all, T it is T is a sigma algebra of sets in the rectangle, in the square in E, and let us denote T infinity sigma algebra of measurable sets in the plane R2. Yeah, no, T infinity is in fact union of its element union of measurable sets in each of these mosaic of unit square covering the plane. So from this picture which was here, I write T infinity is isotropic. Isotropic means that you can turn the coordinate axis and see that if you repeat this construction in the new coordinate which are turned, then we after all arrive at the same sigma algebras in the plane. The I would say chosen directions along x and along y axis which make this thing initially look like anisotropic. So we have some chosen direction. After all this construction, it goes. Yeah, and we have isotropic situation. So the set is measurable irrespective of in which coordinates we work. It can be, and we can even consider, say, polar coordinates, or consider no coordinates at all, only the metric on the plane. Will have the same sigma algebra of sets. But in practice, sometimes we are better with this work in these rectangular coordinates, and this is what I'm going to talk about next. But now let's do the following. I will. It was the first part of my lecture. Let me make a break, divide the lecture in two. So this here I finish about the sigma algebra, and next will be about the Fubini theorem. So now let me stop for a while.